myself, so I got to change my plan. So my presentation today is titled "Anyone Can Engineer." Has anybody seen the movie Ratatouille? All right, and everyone loves Remy, right? So Remy's this rat, and he wants to cook, which doesn't really fit with his background. He puts his entire family's lives at stake to pursue this dream of his. Luckily, if you want to do engineering, there's no risk to your family. One thing Remy has going for him is this passion that he had for cooking. Okay, despite what anyone said and what his life experience was around him, he was able to focus on that and accomplish his goal. And I think anyone can do that wants to be an engineer. Actually, I don't know how to progress slides, so I just... There we go. Okay, so I'm going to tell you a little bit about me. That's me in elementary school. Do I need the mic? I don't think it's working.
It's working. Yeah.
Oh, it is? Oh, okay.
It's just recording internally.
Gotcha.
Yeah,
Okay.
We can hear you back here, though.
Sounds good. Okay. That's me in elementary school. Can you guess what state I'm from? Texas. That's right. Good job. Okay, so I want to talk a little bit about some of my weaknesses in elementary school and high school. I wrote my fives backwards. I had the embarrassing number 5 taped to my desk when I was a kid. I was in tutoring for spelling. And what that meant is my teacher threw me in a corner with a cassette tape with spelling tests running, and I just wrote them down. So you homeschoolers are lucky. I don't think your parents have probably ever done that to you. Some other things that were a struggle. This symbolizes to me a lack of communication skills. So spelling, honestly, is not that important in engineering. You've got spell check, but communication is vitally important. When I was in elementary school, I was painfully shy. I wouldn't talk to anyone. I remember going to McDonald's and there was no straw, and my little sister went to ask because I was too scared, and I was in high school. So communication was not a strong point. But what I did have going for me was, well, my favorites right here was Legos. I played with Legos from the time I was really small. I loved math. Despite my love for math, it was a real problem when I went to college because of some situations at home. We moved, and I missed trigonometry. So I actually had to go back after I graduated from high school. I had to go back to school. I had to go back to learn trigonometry and calculus because I just skipped it. And you can't do calc without trig. So, but the reason I share that is like if you have a weakness there, you can overcome it by determination. Working with tools. My dad had us work around the house. You learn a lot by working at home, just fixing things at home and problem solving. That's problem solving skills. And then we were always shooting off water bottle rockets in the yard and science fair projects. And those types of things teach you how to problem solve like an engineer. So I went from this to this. So this is what I worked on after college. My first job out of college was actually working on this airplane, which is pretty shocking since it was built in the 1950s and 60s. I was a hardware designer dealing with obsolescence. So they designed it for batteries that were invented in like 1965, and you couldn't buy them anymore. And so we had to redesign things to work with equipment that is available, right? This is the F-35 Lightning II. I worked on this shortly after they had built their first prototype. We're going to talk more in detail about that in a minute. No, never was in the military. So I worked for government contractors. So Lockheed Martin and Northrop Grumman and the Aerospace Corporation. This is a rocket, so I work, not to scale, it's a lot bigger than these. So actually, that one was really cool. I was hired by the Aerospace Corporation to be a consultant. So basically, we would oversee United Launch Alliances, because they're the ones who built this. So we would oversee it, and I oversaw some of their analysis for this, for testing their launches and for the structural integrity of the craft. So to teach you a little bit about what you can do to foster engineering, I'm going to walk you through a design problem we had on the F-35. the reason I switched from this to this is because I was bored, which might seem weird. Hardware design wasn't that interesting to me. I love math, and this I got to do a lot of math. So I did structural analysis. So I had to do a lot of math. You need geometry, trigonometry, and algebra were probably the top three that I used in here. Here it was arithmetic, maybe. so much more exciting if you like math. Anyways, so here's a design problem. I just started working there, and they had built the first prototype of the F-35, and they had manufactured some of the second. It was either a second variant, there's 3 variants to this aircraft, or it was, I just don't remember, just a second one of the same airplane. But after they built it, the loads group came in and said, uh-oh, we've got some heavier loads than we anticipated, but you've already built the airplane. What are we going to do? And so as a structural analyst, I had to go back and look at the airplane and find out what we could add to it to prevent buckling failure. So does anybody know what buckling is? You know what buckling is? Yeah, so it crushes it, right? So take this is my airplane panel, okay? And the load is too strong and it makes it buckle, right? You don't want that to happen, obviously. So to do that, as an engineer, I mean, it took weeks of work and a lot of analysis, a lot of math, a lot of teamwork. You had to talk to your systems groups to find out what systems were going through that panel. You had to talk to the loads group, make sure you had the loads right. There's a lot of spreadsheets and a lot of data. I'm going to ask you guys to design a airplane panel, but we're going to do it the easy way, which is not with metal. We're going to use this. You're going to design an airplane panel yourself, and we're just going to test it. We're going to skip all the analysis, okay? So, so this airplane panel, don't worry, I'm not going to ask you to take this kind of thing to your homeschoolers, but I'll show you how to apply it to more home, easier things to do. But, all right, so this is my testing apparatus. It's designed with Lego weights, right? And we'll put our panel in it. And we want to make sure it does not fail in buckling. All right, well, obviously it fails in buckling, right? Okay, so when an airframe is designed, we have to design it in a way that that doesn't happen. And what we add to panels is what we call stiffeners, okay? So like an L-shaped, imagine like an L-shaped bracket, but it's really long. And in the old days, they'd actually bolt it through the web, the panel of the airframe. What we would do, and it was really hard for me to find a picture of an airframe that's modern on the internet. There's probably good reason for that. But a modern airframe is milled out, and so it's a continuous piece. So you have a big hunk of metal, and they mill it out so that you have stiffeners. You know, that's a cross section of it. You have these stiffeners in it. So I have some pictures. They're blurry, because that's the best I could find. So this is the F-35 Lightning II short takeoff, vertical landing version. So there's a lot of loads when you're trying to lift an airplane with a propeller like that. So the frame I'm talking about is in here. Northrop Grumman only worked on the center fuselage, and Lockheed did the rest of the airplane. So you see these green blurry things that go through here? Those are pipes, so or electrical, right? So there's hydraulic systems. I'm saying pipes, but it's probably a hose. And then some electrical things that have to go through your panel. So your panel is going to have holes put in it, okay? So you're required to put 3 holes in your panel. This is one of your design requirements for subsystems to go through the panel, okay? This is another picture. I'm trying to show you that this is a web, and that's a stiffener, and that's a stiffener, okay? This is the only picture I found of an actual center fuselage. They didn't say it is, but I'm 99% sure that's the F-35 center fuselage, and those are that's the actual airplane panels. So that's a web, and then the thicker part, obviously the stiffener. Anyone have any guesses how I make stiffeners in my paper one? Any ideas? Don't have any tape, no tape. Let's pass these out. I want you guys to work in teams, like maybe 2 to 3 people. So I should just, I'm gonna make you guys pass these around. Here. Find a partner. Hopefully I have enough for every 2 to 3 people. Just take one and pass it around. You guys want to take one and pass it around? Oh.
I'll allow it.
You're supposed to add things to it or just use the card itself?
No tape. I'll tell you that all that stuff in just a minute. There are rules, so don't bend it yet, guys. Okay. So this is the engineering design process. So does anyone know what our problem is we're trying to solve? We want to what? Prevent buckling. All right, we want to prevent buckling of our airplane panel. Okay, we have some constraints, and guess what? You have to talk to people. You got your teamwork, and you talk to people to find out what these are. So I'm just going to give them to you, but in real life, you're going to have a design engineer that you work with, and you'll have to communicate with them. So I just want to run through the whole thing, and then I'll get to what the details are, okay? After that, you do research, and you find out more details about the subsystems or more details about buckling. Maybe you don't remember Euler's formula for buckling, so you go ask your neighbor, okay? Because you're in a whole group of structural analysis nerds. All right, so you research this, and then you brainstorm ideas. You talk to your coworkers, you talk to your manager. You design a prototype. You tell the designer what to do, and he designs it. And then you have to test it. I don't think we tested it on the airplane eventually, but that's a long process with the F-35. And the whole time you're communicating, and most engineering design process will have an extra section that is communicate. I put it through the entire thing. But it's very critical here because you're gonna have to go tell your boss or the chief engineer, and he's not nice. So he is very interested in how you got to your conclusion and if it works or not. Because I know a lot of times when you think about engineering and maybe product design, you might think their goal is to make money, and yes, that is their goal. But I never heard anyone talk about that at our work. I mean, most of us are just working there, right? We are always concerned about the life of that pilot. So we have a man's life a man's life at stake, and $1 billion aircraft, right? So I just threw that number out. I don't know if it's probably not accurate, but it's expensive. Okay, so here's our process. We identified the problem. We want to build an airframe that withstands buckling loads. We do want it to be as light as possible. I'm not sure we're going to get much progress in that because I've simplified this. I usually use paper instead of cardstock, but I didn't want to cut all these pieces of paper. Anyways, because you can make it even thinner and lighter. But okay, it looks like I said 2 holes. So our constraints are we need 2 holes for our subsystems. Minimum size is 6 millimeters, so 6 millimeter hole punch. The finished panel size has to be 3 inches by 4 1/4. Got rulers. And there's scissors, there's a hole punch, and 3x5 cards as our materials. So those are your constraints. When you're problem solving things at home, just talk about this. Just talk about those words. Use that language, and they start learning it. If you're more deliberate about it, because you're problem solving constantly, right? Just be deliberate about it, okay? So, okay, we've done the research. We've already learned about buckling. And then I want you to brainstorm solutions with your partner, okay? Why don't you guys talk for yes, go ahead.
So the finished product needs to be 3 by 4 1/4.
Yes.
Right? How big are these?
These are 3x5. I actually didn't measure them. I'm hoping it's not like a 2x4, and that's the nominal dimension. But so if someone wants to measure, do you want to measure yours real quick? Let's see what it is. Yeah. So brainstorm with your neighbor how it's good. Okay. Perfect. I was thinking about that this morning. I was like, maybe it's like a 2x4, and it's not actually 3x5. Okay. All right, brainstorm for just a minute, and then I'm going to pass. I only have 3 hole punchers and 3 testing things, but all right, so what kind of skills did we use to solve this problem? Origami, right. Spatial visualization, that's what you said, right? We didn't use any math, really. Oh, we did use math. We did measuring, right? Was communication important? Yeah. Not for yours. Why was communication important if it was important to you?
Because we had a team. Because you could learn that you had a better idea than someone.
Kind of. I mean, they might have a better idea than you, and you can help each other, right? All right, and that has to do with teamwork as well. And then obviously it was problem solving, which is engineering. Engineering is problem solving, right? Okay. So spatial visualization is my favorite part of engineering, and it's actually really important. And usually for people who like engineering, that's fun for them. But for some, it's not. There's actually a study done at Michigan Tech by a professor there who has a PhD in mechanical engineering and almost dropped out when she was a freshman because her spatial visualization skills were really bad. Okay? So she's done a lot of work with that and has actually created a program. It's free. It's just like online lesson plans and things. It's designed for college level, but I went through them and it's right here. There's some great lessons in there that you can easily modify for kids. Like, for instance, one of the lessons was you take an apple and you draw the top view of the apple, you draw the side view of the apple, you cut it open and you draw the inside. And spatial visualization is the ability to see an object in space and how it relates to other objects. And that's critically important in mechanical engineering, obviously, but also chemical engineering, electrical, all of the tech sciences. My father studied chemical engineering, and I called him as part of this, and he said, he told me about a problem he had on one of his assignments where they had all this technical data about chemical things, right? And then the professor asked, well, how large of a diameter can the vessel be? And none of the data had anything to do with it. What it had to do with was communicating with a sub-team and also looking at how would the truck get the vessel through the roads. So it was all about how big the item was. So it's also interesting is that women are actually worse at this than men. They've done studies on it. So they're not sure exactly why, but at Michigan Tech, they test all of their incoming freshmen for spatial visualization. And they did a study. The ones that failed the test had the option to take a class that taught spatial visualization or not take the class. And of the ones who took the class, it increased the graduation rates of their women by 21% and men by 7%, which is pretty incredible. And that's not just mechanical engineering, that's all of their tech programs. So this is, I remember taking this test when I was in college. Basically, you'd see this object. It's twisted. Which way is it twisted? Like this, right? To go here. Take this object, twist it. What does it look like? A, B, C, D, or E. And it's just a bunch of questions like that. And that's the test that they do. And it was made in the 60s and they still use it. So it's by Purdue. So that's something you can work on at home. And there's some fun ideas here. I just wrote down a bunch of things that I think really help with spatial visualization. Drawing and writing helps with spatial visualization because you need the space between words. Don't write your fives backwards. That can be, it's not always, but it can be a spatial visualization problem. Take things apart, put them back together. Building with instructions, I'm an engineer, I love the without instructions part, but I've noticed as I've worked with younger kids, they really struggle with spatial visualization. Some younger kids, you might not. Good, you're on the right track. Pioneering projects, is anybody here part of Scouts? They have the pioneering projects when they take those gigantic logs and they tie them together with rope and make structures out of them. And that's a good exercise. Games, there's a lot of games that can help with spatial visualization. Okay, math, this is just I think math, you can find a ton of information about math, right? Tons of information. In general, most engineering degrees require, you should probably take these in high school. And like I told you, I missed trigonometry. I took calculus, but I didn't learn much because I didn't know trig. But in college, this is what some of the engineering requires. Is probably the maximum amount of math, which is a lot of math. Mechanical has to do all of this. Chemical does. Electrical definitely. But some of the other engineering programs might only take you to Cal 3. But from my experience, this is what's used the most. But everyone's experience is different, you know. Communication. All right, and then this is where I don't like my presentation anymore because I have things, and I started to realize all of them had the same list over here pretty much. There are maybe some slight changes, right? So I think I should have actually reworded it as in use the list and then talk about why those help these things. But most projects are going to help you develop communication, teamwork, and problem-solving skills, right? Especially like if you do family projects. The other thing that really helps is family disasters. Have you ever had to use problem-solving skills in a family disaster? When I was a kid, we went camping and forgot tent poles. So perfect opportunity to work on the engineering design process. What materials do you have available? What's the problem you're trying to solve? Communicating and building your tent with your lawn chairs. So there's always opportunities for problem solving. And I love camping and scouts for that because they're not artificial, right? Like you get yourself in a situation and you're in the forest or you're far from Walmart, like you have to figure out what you can away from those helps. But I also like, things like this. That was very artificial, but really fun, right? Okay, and I'm not gonna read the list because we're out of time. But teamwork, I just have some pictures. There's a pioneering project at Scouts, if you didn't know what those are. I have a kid whose family's building a chicken coop right now. That's perfect opportunity for problem-solving skills, using tools, learning how things work. First programs. So I do have 2 teams myself, but anyone can do first. I mean, anyone can do first. It's a lot of work, but you can do it. Let's see. And then, of course, family adventures are always opportunities for teamwork. Sports, I don't really know if it translates well. When I first wrote this, I put a question mark because I'm not into team sports. I think it helps some, but it's a little bit different than projects. It's a little bit different. Problem solving, it made me think of a farm. Does anybody have a farm or a homestead that they go to? Or this is my uncle's farm, and at problem solving, he had to put these posts in, and he has this gigantic tool, and you can do it really easily, a lot better than doing it by yourself. Okay, that's good. All right, so this is just the same design process. Using that with your family when you try to solve problems can help. And then the rest of this is just lists that maybe I can just send this out, but take a picture. A lot of people ask me about Legos, like what Legos to get, and I like all of their education sets. They're really good. But even regular Legos are fantastic, especially for your younger kids. I mean, they're just absolutely fantastic because they're walking you through, turning things around and looking at them on different sides, which is what spatial visualization is all about. And when you're an engineer, you're writing instructions, just like Lego instructions, right? Often, right? Okay. And then here's some resources that I found. It might be fun to take one of these spatial awareness quizzes, see how you do, see how your kid does on spatial awareness, and then think of some ideas on how you can improve that. Does anybody have any questions? Oh, first, let's see. I don't remember what the acronym means, but it's a organization. It's a worldwide organization that does robotics competitions, And they have them for really little kids, like kindergarten age up through high school. So I do first Lego League at Code and Bots. There's a lot of like homeschool groups might do, or schools often will have a first Lego League team. High school in the United States is what they call FRC and FTC, also run by First Tech Challenge and First Robotics Challenge. And what's so fantastic about those programs is you're doing everything I talked about here. Like, I mean, the reason I started doing it, I'll tell you a real quick story. I was doing mechanics classes at my son's elementary school, and the principal called me in and asked me to do a robotics team, and I just kind of laughed her off because everything I'd ever seen outside of engineering that talked about robotics was just a remote-controlled car, so I didn't think it was real. And I went home and looked it up, and I was in her office the next day and told her, we're doing it now, I'm the coach. and then we went for it because everything those kids are doing is exactly the same thing I did in college, except with Legos. It's exactly the same. I mean, as close as you can get, right? They talk about, they have a chief engineer. At least in my team, we have a chief engineer. I don't know if all teams do that. But they have to present in front of judges, which is like presenting in front of your boss at work. And it's a really difficult challenge. It's just Legos, but it's really, really difficult and a really tough competition. It takes a lot of mechanical engineering and physics and math to accomplish their goals, and it's just with Legos. It's just pretty fun. So, yeah. So, thanks for coming. I hope that helped a little bit.